Okay, let's get back to our class. So I think I basically just discussed about the observation that because we are talking about the delta here, so this delta is actually returned to be the minimum of the two recursive calls in division. Actually, this just suggests that we're probably not going to have like vertices that are super close. I mean, this is just going to violate the definition of delta here. So this is actually a key observation that we can turn this rigorously. And actually, the thing that we are going to prove is that if I minus j, I mean, if they are larger than 12, then the distance between S and Sj, they're actually going to be at least delta. So let's actually prove this. So the proof here is actually by looking very closely to this delta strip. So let's actually draw this larger. So this is delta. And actually, this is delta. So we actually draw, I mean, even smaller, I mean, squares. So we consider such kind of squares. So we consider such kind of squares. So we draw squares of size delta over 2 times delta over 2 in the delta strip. So a fact is that no two lie in the same square. I guess this is the reason why we want to take a very close look at this. I guess here, the drawing here is a little bit tilted, but I really mean, they are like squares. I mean, delta over 2, delta over 2, delta over 2. It's really something like this. So no 2 points lie in the same square, because for instance, if you have, even if the 2 points like this, their distance is of course going to be smaller than delta. And actually this well is the definition of the delta here. And actually, this is, maybe let's just call this fact 1. And the second fact, excuse me. So the second fact that we are concerned here is that no 2 points, or maybe let me actually tweak the English a little bit. So 2 points at least 2 rows above have distance at least delta. I mean, for instance, let's assume like a vertex, maybe for instance in this first layer, and then you consider maybe some vertex in the fourth layer. First layer. So if they differ, by at least 2 layers, the distance should also be at least delta. So this is also something we actually clearly see here. So I guess these 2 facts should be relatively straightforward, right? But actually, this gives us the conclusion here, because if you consider this, each layer has 4 squares, and looking above, at most 3 rows are relevant. For instance, assume that this is your SI here. So you only need to consider, this box, and also all in this row, and this row. For the other boxes, squares are above that. You know that their distance should be at least delta. And actually, because we already know that the delta is actually our answer, so you don't need to really worry about that. And actually, there are at most, 12 boxes here. And actually, that is the reason why we have such kind of key observation. So I guess this is relatively straightforward, but is this, do you have any questions about this? Yes.
the emails exactly by is the two. So it's the same two. If the column is next and the next.
But you want to be specifically careful here. I mean here maybe you are worried about like this vertex and this this. I guess maybe you are talking about like 2 points like this. I guess maybe, or like, I mean, what do you mean by columns?
Yeah, I mean, when we need to consider 4 columns and 3 rows, it's not symmetric.
I mean, it is indeed not symmetric. I mean, but here the thing being not symmetric is the left and right. We are not talking about up and down. We are talking about left and right. So here the row here being 3 rows is basically we need to because the row here really corresponds about like the vertical distance. I mean, from if you have like a vertex like this and also like this. This really is not actually going to help you. I mean, actually, because you know, basically for the left-hand side, it's already delta. But I think here, I mean, in general, I mean, I can make a remark here. A careful analysis can improve output. Yes. So there are some very like intricate argument, and if you should to take a close look at everything very rigorously, and actually you can imagine that you actually don't need to worry about this and this because this distance is at least like square root of 2 times delta. So this is not so important. But in general, I mean, it is indeed asymmetric because the row and columns they are different because you are talking about like partition between left and right. I mean, you can also, I mean, at the very beginning doing divide and conquer, you just like cut in the two y-axis. That is also fine. But here, I mean, I just make a safe argument to make sure everything works. Oh, sure. You're welcome. Any other questions? So I think, I guess maybe if you still have questions, I think nevertheless, maybe let me start to write down the algorithm here. I guess basically this 12 result, I mean, or maybe if you're very careful, it is known that this can be improved to 7. I mean, you can check some research paper on this. But nevertheless, I guess maybe this is more like an analytical thing. And I think the observation is just to make sure that as long as your coordinates according to, I mean, the points in this delta strip, and you should store them according to the y coordinate. So basically, as long as this is good, you can actually, I mean, the distance at least a constant. I mean, no matter it's 12 or 7, it is not going to change the story about log. It's actually going to give you a good result. I mean, basically for this divide and conquer. Actually, write the final algorithm here that we are going to consider here. So the algorithm closest pair. Maybe that's called the word to be P1 to Pn here. The first thing that we will do is actually we will compute the separation of line L such that f the points on the left-hand side and half on the right side. So let's say like delta 1 is maybe, for instance, like closest pair. So because we are making the division here, we can call this left half. And maybe delta 2 here, let's call closest pair, which is the right half. And actually the delta that we use above is just like the mean of delta 1, delta 2 here. So the remaining part is basically the merge. So basically this combine. So we need to delete. Let me actually do this. So delete all points further than delta L. And actually we sort the remain. Maybe let me actually for the remain part use the sort the remain. By y coordinate. So the last line is basically the crucial line that we are actually going to make the merge. So we scan points in y coordinate ascending order and compare the distance between each point and its next 11 neighbors. So if any of them this distance is less than delta, the delta. And the thing that we will finally return is delta. So here, I think a very quick remark is that we can not only return on delta, but also the pair that reach this. Just like keep storing this. I mean, this, you just take another register to keep storing this with the delta pair. And each time you refresh your register, just like also refresh the corresponding pair. Keep storing this. I mean, this is just like a very standard trick. I mean, as long as we can, this algorithm works correctly and you can up the delta here, you can actually take this ahead. I mean, all this. It's all this. So this is basically the closest pair algorithm, and maybe let's take a look at the cost of this algorithm. So in particular, I mean, we can actually say that basically basically, I think we need to have for this part, actually it has a cost of O of n log n, because we are talking about like the half points on the left-hand side and also half on the right-hand side. And basically this requires a sorting. And basically for this, I mean, for this problem, I mean, the divide is not totally trivial. I mean, the divide part is that you really need like a pre-sorting of all the x-axis and also a sorting of all the y-axis. So basically this cost is like O of n log n here. And actually for this for these two lines, and actually this is going to give you 2 times t of n over 2 here. Delete all points further than delta from L. This cost is just O of n. You just like you just go, because you have like a sorting, you just go through all the vertices. I mean, from left to right, for instance. I guess this is just relatively straightforward. You can just check all the vertices. And basically, I think another sorting part is like the remaining points by y coordinates. This is O of n log n. And actually scan through the points. I mean, just check the distances with the next 11 neighbors. So this is just also going to give you another cost. I mean, no matter it's like 12 times n, 11 times n, or 7 times n, this is O of n. So this is actually not good for us. So is this algorithm and basically this right-hand side, basically this right part, I mean, basically analysis of the time cost clear to you? Okay, so what does this gives? I mean, at the very beginning, I mean, this sort is more like a pre-processing step. I mean, this is not really relevant to the, I mean, I shouldn't say it's not relevant to divide and conquer, but you can just regard this as the beginning, you have this cost of n log n, you just like sort all the vertices and you know its corresponding order. So this is basically something we are good with. But basically for the other part, I guess, especially for this line, you can see that this is actually a line that is a little bit expensive. I mean, after we have deleting all the vertices further than delta from L, it seems that we are here actually sorting the remaining vertices again. But actually, maybe we can think maybe further about this. It's actually, this is necessary, that actually we need to pay this log n factor. So actually the answer here is this part can also be of cos O of n here. So why can we do this? So we just like here, both pre-sort x and y here. So because we can actually in this pre-processing step, we don't need to each time we like make a sorting of about like all the vertices of y they're actually concerned with. I mean, you can just at the very beginning, you just have two sorting lists. I mean, it's like two cos of O of n log n. You sort all the vertices according to their x coordinate, and then you sort all the vertices according to their y coordinate. You take this two lists in hand, and then you just like do the divide and the conquer. And basically in this part, I mean, basically now in this part, I mean, for the remaining points, you know, like remaining points, for instance, it is the, I mean, according to the x coordinates, maybe it's like the first vertex, maybe it's like the first, second, and like fifth, for instance. But you know, like a corresponding ordering of like the corresponding y values. You just like look at your table and basically you know actually what is the corresponding sorting. So this is actually a very important point that actually throughout this algorithm, you don't actually need to take all the costs of this sorting, I mean, throughout. And actually what is inside this algorithm, inside the divide and conquer. The cost is basically still T of n equals to 2 times T of n over 2 plus O of n. So is this clear to you? And actually this just gives like close x pair x cos O of n log n. So this basically finishes the discussion of the closest pair problem. I mean, maybe it's not. I mean, at the very beginning, this is probably. I think from my perspective, I think this problem of closest pair that can be reached to cos of O of n log n is probably more surprising than sorting and actually counting inversions, because this problem, I mean, you move from one dimension to two dimensions. Maybe you want to think about okay. I mean, it's probably. I mean, this point. I mean, probably you really need to check a lot of pairs to really get sure about like what distances are between them. Actually, you want to find the closest pair. But actually, I think a very key argument here is basically this geometric argument that actually you clearly define what is delta here, and basically you utilize the property of this delta here. And actually, in this, you don't really need to check a lot of pairs. And actually, based on this key observation, actually throughout this algorithm, and also the observation that you can actually pre-sort this algorithm a bit. And actually, you can give an algorithm that finally the cos is actually O of n log n. So any questions?
Or if the weights have higher dimension, will the
Oh, that's it.
modify
We need to modify that. This algorithm does not work directly work in the 3-dimension. So, but in general, I think for the high dimensional case, the closest pair problems is in general quite difficult. I mean, also for instance, I mean, in some other problems that we are actually concerned with, for instance, like, I mean, this in general belongs to the category of like geometric algorithm. I mean, some kind of geometric data structures are very important in big data. I mean, in general, I mean, if the dimension is D here, it is very difficult to get rid of the curse of dimensionality. So you get a bounding terms of D here.
because we need to solve in each dimension.
Yes, basically. Yeah, that is already something quite really, I mean, really heavy in general.
I think 3 is still not so hard.
Yes. I'm not, let me see. I kind of forgot what is the cost for the 3D case for the closest pair problem. But I would imagine maybe the cost is around like n squared or something like that. Yeah, I'm not totally sure about this. Maybe you can check the literature. I think a lot of algorithms typically they have costs. I mean, in terms of D, like D over 2. I mean, some like n to the D over 2 or something like that. I think basically, I mean, this is only like an introductory course, so we don't want to get into like super details. I think we focus more on like the spirits, like the concepts of like designing algorithm here. And actually, already the thing that is very cool for this 2D closest pair problem is that it somehow is like a mismatch. I mean, for the 2-dimensional problem, I mean, the cost is linear in n. So here, that is already, I think, a great lesson that we can learn. I think, in general, for the high-dimensional cases, more complicated. So you seem a little bit confused. So, any questions? basically like, for instance, maybe we can, maybe some example like, maybe like this n to the 12 case. Yeah, so sure. I think maybe we can just like go into this n to the 12 case. I mean, this is just like I mean, you can just imagine like, I think Taiwan also asked a question about like this example during the break. So just imagine how you're actually going to work with this. So in general, for a lot of problem in big data, maybe you can just assume that for the basic case, I mean, maybe for instance, you only have like 3 vertices. I mean, this is not so difficult to just like check all the 3 pairs. So let's, for instance, like divide into like this. I mean, you have a case where n equals to 12. So you divide them into, you actually divide them into 2 cases. And basically, the left-hand side has 6 vertices and the right-hand side has 6 vertices. And actually, in the recursion, you still need to call the closest vector pair. So you see here, I'm actually drawing like an L, like an L here. But for the left, I mean, it's actually I mean, maybe let me draw a tree like this. So n equals to 12. So you have the left part and the right part. Actually, where n equals to 6, actually n equals to 6. I mean, you can keep to call this divide and conquer. You still have the left where n equals to 3, and actually n equals to 3. So you actually here, you actually go really going to bottom, and it's not very difficult that you can, for the small case, basically the call is all of 1. So, but here, so basically this part is the left. And actually you can just brute forcefully check. I mean, for instance, like this is the shortest. I mean, you can also, maybe for this left to right, you can see like this is the shortest. I mean, let me erase this because this is not originally there. So here basically this part is the right left is basically, I mean, this is the left and this is the left right, and this is the right right. So this is basically what I mean here. So basically for this right left part, so we can just take a look. I think this, they really have like a long distance between each other, but I guess maybe this is shorter. Say. So now I think finally we take a look at the right part, and actually this is basically the right. So this is basically these are two examples, and actually basically these 2 intervals are actually in the recursion where you call the left instance at the very beginning. But here actually you take a look at this and you have this, and basically you run the algorithm and actually you check in the middle here. So here what you mean you check in the middle is that okay, so here I guess this is like the delta. I mean, let's call this delta lab. So this is the delta that is the smaller one, and you just like draw this. I mean, roughly speaking, I call this like delta. I mean, I guess in this case, this is probably a very easy problem. I mean, there is just like no vertex inside this delta strip. And then you just finish, you just return left. I mean, here, because I said that you return the best of the 3 solutions. I mean, there is no solution in the merge, and the right is larger than the left. So you just like return. I mean, for this, I mean, it's just like you finish this level of recursion, you actually go back to this. Actually, we know we are good. That basically, okay, you're good. Basically, for this recursion, you know that the answer is actually this pair. And similarly, you can do it. I mean, you can do this. I mean, you can do this for the right. And actually, you know, I mean, in our algorithm, you have already finished the sub cases. I mean, the left case and the right case. And actually, you know, this is actually the closest vector, and you correspondingly draw the delta strip. Maybe for instance, it's this delta strip. Okay, so here in this case, we have 1 vertex here. I mean, we have 1 vertex in this delta strip, but it is not so helpful. I mean, you need to have like maybe for instance, assume that maybe you have like a vertex here. I mean, this is really going to totally change the problem, because in this case, I mean, the merge is actually going to give you the answer that this is the shortest. But in the original case, I mean, you only look at this delta strip and there is only 1 vertex inside it. So this is actually not so helpful. I mean, this merge is also not to give you an answer better than the left or right. And here you see like the delta that we determined, which is basically this was the delta right. And actually this was the delta right, and you know, okay, this is cool. This is cool, and you're just like, oh, excuse me. You just like remove all of this. Okay, you know that is good, and you just erase this and erase this. Oh, excuse me. sometimes there is bugs when you utilize this again. So this basically gives you the case where you finish the recursive calls, and basically it is the final merge for this very root case. Okay, so here, I mean, this delta, I think the left-hand side is probably a little bit smaller than the right-hand side. So basically, this is the final delta that you are actually currently assigned here. And actually here, you draw this strip. Questions?
No.
Oh, okay. So here you finally draw this delta strip. Okay, and you see like in this delta strip, you have two vertices. And basically what we actually do, I mean, for instance, if you have, I mean, you have other vertices here. So basically we have this y coordinate order. We go from bottom to top. But actually, we know that this is, I mean, the ordering, this is not something that is going to change. I mean, for instance, assume that we know that it is, I mean, x1, y1, x2, y2, etc. So basically assume that basically the point with x2, x1, x2, x5, they pop out. You know a corresponding order of y here. Maybe previously you know that actually the corresponding order is that basically like y1 is actually larger than y5, larger than y2 here. This is basically an order that already gives you. And actually, if you have like pre-order this, you just like scan through this from top to bottom again. And actually, this is the reason why I say, I mean, you just like scan through all the vertices, and actually just for this part, you actually get a cost of ON here. So let me actually just erase this. So you know this by a pre-sorted list, you can check this, and basically for cost of ON, you can check all the neighbors. I mean, for instance, let me just like me go with this complicated case where we have like 4 vertices. So you have this vertex, you check its next 11 neighbors. So this, and this. That is quite far. I mean, and also check this. I mean, you start to check this, and these distances, I mean, these distances, they are really quite far. But the point is that if you go to this vertex and check this next neighbor, this is something smaller than delta. Let's say, I mean, this is, I'm probably not drawing them close enough, but you can imagine maybe it's like this. You start from this vertex and you check this next 11 neighbors, but actually this neighbor is already give you a good answer, and actually you improve this delta, and then basically in all of these checks, all these distance are actually larger than this one, and this delta is just like final answer, and this finish there. Is this actually getting better?
You call that line again? It's called a delta strip.
A strip. I just use this English word.
So the delta, so the value of delta depends on current delta value.
The value of delta here, the value of delta here is the minimum of the 2 recursive calls. Right. This is very important. Basically in this observation, basically in this this key observation. Because you have the 2 recursive calls and you know what is the current mean of the left and the current mean of the right. And this is also the part you see in our algorithm. That is the part where we denote the delta to be the mean of delta 1 and delta 2. Okay, so is everything clear to you? Okay. So I think we basically have 20 minutes, and I think I think I probably cannot reach all of the things I want to talk about today. Oh, actually, I think I can talk a little bit about integer multiplication. So let's do that. I think I probably cannot reach matrix multiplication, but let's start with integer multiplication. Okay. So this is I mean you can imagine that, I mean, you have like a computer, I mean, like basically like adding, I mean, like basically addition, subtraction, multiplication, division. I mean, this is just like so like simple and also so fundamental things that we really want to take specific care of. So let's consider add. I mean, for instance, assume that you are given 2 n-digit integers a and b. I mean, it's just compute a plus b. I mean, here for the ease of our life, I mean, here digit, I mean, digit refers to binary digit. I mean, it's fine that you want to consider maybe some decimal digit. I mean, but there is no significant difference. It's more like a difference between log 2 and log 10 with the base of 2 or 10 here. But I guess basically because we are talking about computer algorithm, makes more sense to talk about like binary digits. So I mean, I guess for adding numbers, I mean, you can just imagine that this causes just theta of n. Again, this is relatively straightforward because you want to manipulate some number. I mean, you really need to look at what the number is. So the cost should be at least linear in n. But adding two numbers is just like bitwise adding. You're just like going from n to start. I mean, for instance, I mean, assume that you have like this number. For instance, I mean, this is binary adding here. This is probably a too simple example, but maybe let's do this. I mean, for adding here, the cost is simply linear in n here because you're just adding from whole. So here is like 1 plus 1, here is like 0, but you have like another going to another digit, and here is like 0 plus 1 plus this adding here. So this is going to give you a 0 and then add here, and like 1 plus 1. And together with this one is going to give you a 1 here. And like 1 plus 0 here is like going to give you a 0 with a plus here, and this is finally going to give you this. So you can clearly see that this cost is basically just theta in n actually. Look, of course, there are clear lower bound. I mean, you need to go through the number to do the addition, and also from back to I mean from n to beginning. I mean, just like do this addition. The cost is just like theta in n here. So this is a relatively straightforward. But how about multiply? So basically, let me just like copy this part. So given two digits, n-digit numbers a and b, let's compute a times b. So I guess in this case, you can probably see that the brute force way of doing this is going to cause n squared beta operations. I guess this is because basically you multiply an n-digit number with an n-digit number. It's basically you need to multiply, for instance, like the first number with every bit of the second number. And this really in general is going to take you cost of n squared. I mean, the question is that how to improve this? So I think this is basically the part where we need to be and in general, maybe we want to have a good strategy about using the divide and conquer here. So let's think about, I mean, for instance, if we want to apply the strategy of divide and conquer, what we are actually going to do. I mean, we have n-digit number. So basically we can, maybe you can divide this into two parts. I mean, each part with this, so like n over 2 digits. So if we do that, I mean, for instance, assume that we have a current input, maybe let's call it to be a here. So your a here is basically equals to 2 n over 2 times a1 plus a0, and your b here is basically something like this. I guess this is basically assume that I have an a here, maybe like this part is a1, and this part is a0, and b here is that this part is b1, and this part is b0. So basically, if you want to consider like a divide and conquer strategy for the multiplication here, you divide in the middle. That is just basically saying that each part is going to have n over 2 digits. And for the first part, I mean, if you consider like the final number here, you're actually going to multiply by a factor of 2 to the n over 2. It's just like just like due to binary representation here. So this is a very straightforward thing. I mean, if you want to consider like a divide and conquer here, maybe let's take a look here. So we know that a equals to this and b equals to this. So what is their multiplication? Their multiplication is going to be a times b. And let's do a very quick calculation here, and that is actually going to be this actually times this. So we can actually make a rearrangement here. So this is actually going to equals to 2 to the n times a1 b1 plus 2 to the n over 2 times a1 b0 plus a0 b1 plus a0 b0. I guess this should be clear. Okay, so if we just consider like, I mean, this is relative, like a relatively straightforward strategy. So here we can say that we are multiplying 4 1 over 2 digit numbers. And after that, what we do is that we need to add 2 over 2 digit integers. So basically, this part, basically we need to add 2 over 2 integers. And basically we also need to shift to obtain the result. I mean, basically by shift, it's just like we have this 2 to the n and also 2 to the n over 2 here. Basically, we need to shift the corresponding, I mean, we need to add the corresponding number of zeros after that. So that is basically the thing we are actually having. But actually the heavy part, I mean, because we are doing divide and conquer for the multiplication, the heavy part is that we actually have to multiply 4 n over 2 digit integers. Basically this a1, b1, a1, b0, a0, b1, and also a0, b0. So we are actually multiplying them. So this is the part that we actually need to pay specific attention to. And I think from this perspective, you can imagine that the cost of our divide and conquer algorithm is going to be T of n equals to 4 times T of n over 2 plus n o n. So basically, this is going to be our recursive formula for the current divide and conquer approach. So is this clear? Sure.
A1 might be B0, maybe digits.
Yes, that's true.
So the second one should be
Oh no, I mean, I think, sorry. Yeah, I guess here, yeah. It should be written as n here, but does not make a big difference because after adding is taking linear time. Yes, sure, sorry. So I think the main focus is basically this recursive formula. So do you have any questions about this recursive formula? Okay, so if there is no question, let's think about how we want to solve this. I mean, in general, recall that when we solve this, P of n equals to 2 times n over 2 plus O of n. I think a way that we actually to solve this recursive formula is that we make this formula homogeneous, that basically we divide an n in both sides. And actually after dividing an n here, this becomes n over 2. And actually this becomes O of 1. So here it is a 4 here. I mean, if you just divide it by n here, this is n over 4. But this is probably not as good looking as the previous part. So what is the corresponding solution that maybe we can think about? I think maybe we can think about dividing n squared here. So why do we want to do this? This is actually the part we are actually making it homogeneous. So if we divide it by n squared, and this is basically n squared over 4 here. But n squared over 4 is simply n over 2 squared. And actually this part is, because you are dividing n squared, this part becomes from n, and you reduce this to 1 over n. So this is clear to you. So this is probably not so good because we can just think about what this look. This is actually going to look like T of n over n squared. And this is equal to T of n over 2 divided by n over 2 squared plus O. Actually, this equals to T of n over 4 divided by n over 4 squared plus O of n over n plus squared. So finally, this is actually going to give you, I mean, assume that basically this is like this O of n is basically like C times n. So this is basically going to give you like a C times like n over n plus 1 over n over 2 plus 1 over n over 4 plus plus 1. And we know that this is basically a geometric series. So basically just imagine this is like 1 plus, maybe let's look at in the other way, 1 plus a half plus 1 over 4 plus 1 over 8, etc. In general, this is basically speaking, this is smaller than 2, smaller than 2. But nevertheless, this is not so helpful us because we are showing this value of T of n over n squared. And this is just suggesting that T of n is actually something theta n squared. So because basically we know that actually at the adding part here, it is theta. This is actually theta. And this value, because finally has a 1, it must be between 1 and 2 here. So, I mean, although it's like smaller than 2c here, it is actually just like a theta of constant. So that's the reason why I'm saying that basically T of n is theta of n squared. So this is not so helpful. Same as brute force. Okay, so I guess you are probably not going, maybe let me, I think it just got stuck. I guess you are probably not going to be satisfied if I'm only mentioning this. I mean, this is not so helpful at all. But maybe actually we are actually not using like the best strategy here using, I mean, actually in this divide and conquer approach. Maybe you can have like a more clever strategy that we use the divide and conquer approach. So actually a specific thing is that maybe let's take a second look at this part. So let's take a second look at this part. I mean, this equation is of course noticeable. I mean, this is definitely correct, but maybe, I mean, you see like A1, maybe let me, yes. A1, B0, and actually plus A0, B1. It actually has some sort of correlation with A1, B1 and A0, B0. I mean, this is in the middle, and this A1, B0 plus A0, B1, it is not something, I mean, totally independent of like this A1, B1, A0, B0. And maybe you want to have like a better way to represent this, and hopefully maybe such kind of representation can give you like a clever idea along this. So basically, this is the key observation along this, and maybe you can take a look at this equation I'm actually writing here. So here I'm actually not using A1 B0 plus A0 B1. I'm using this. I'm using A1 plus A0 times B1 plus B0 minus A1 B1 minus A0 B0. I guess this should be correct to you, right? So here, let's actually use some letters here. So let's call this part to be A here, and let's call this part to be B here. So this is another A here, this is a B here. And this is some multiplication that is different from A and B here, and this is actually a C. But a very made observation by this inequality, by this equality. And actually this is actually first observed by Karasuba. So basically made this observation, and actually now to multiply two n-digit integers, we are only actually multiplying 3 digit integers. So here we are not fully rigorous because we are talking about A1 plus A0 and B1 plus B0. So here, to be honest, this should be an over 2 plus 1 digit. But again, this is actually not going to influence our analysis by a lot. But maybe let's actually take this rigorously here, and let's look at what is the next thing that is going to happen. So next, we're going to add and subtract now, because here we do have some subtraction here, so we want to be a bit careful. But as you can imagine, both addition and subtraction is actually going to only take linear cost. You just like do it bitwisely. So this is not so different. So you just add and subtract 3. Let's say let's say at most n digit integers and shift to obtain the result. So we take this observation that basically, I mean, this A1 plus A0 and also the multiplication between A1 plus A0 and the B1 plus B0, they have at most like, they can have like n over 2 plus 1 digit. So the recursion here that we actually have is basically T of n. It's now smaller than T of, I mean, if we don't even further take the assumption that n is a power of 2, then rigorously speaking, it is more something like this. So it's basically a T of n over 2 a floor function plus a T of n over 2 ceiling function plus, let's say, like T of 1 plus n over 2 ceiling function plus an O of n. So for the ease of our life, let's study the relationship T of n smaller than 3 times T of n over 2. So this is not actually going to make a big difference. Okay, I think I'm basically running out of time. I think I have basically at most 3 or 4 minutes. So I think maybe let's write down the conclusion here. I think maybe let me actually give a theorem here. Maybe it's just to give you the answer, and we are going to show the details that time. Actually, T of n equals to n of log with 2 of the bases and 3 as the function. So it's basically n of log 2, 3. And roughly speaking, this is O of n to the 1.5. It's actually, as I just mentioned, this is first observed by Karasuba. And actually, this is formally known as a result by Karasuba and Hoffman. Yeah, paper about like 60 years ago. That basically we can multiply two integers in cos of n to the log 2 of 3, which is basically log n to the 1.585. So basically in the next class, we are going to prove this. And actually, this is only for integer multiplication. And you can just imagine the algorithm, I mean, it's probably not integer multiplication. Next class, we also carry matrix multiplication and basically some relevant discussions about like numerical, basically about numerical analysis and also a linear algebra. But I think as a quick recap, I think basically today we have been talking about basically this is the start of the divide and conquer discussion that we talk about. This also a very important strategy of design algorithms. So the first example that we talked about in this class is basically the Mergesort example. So basically the sorting is like one of the most important problems in algorithm design. And basically we can see that divide and conquer gave a relatively simple algorithm for sorting with cos O of n log n. And correspondingly, it's still about like arrays. And basically we can not only sort, but we also count like the number of inversions basically in these arrays. And then we talk about like a very interesting geometric problem of finding the closest pair of points. And also, I think due to time limitation, we haven't fully covered the details of integer multiplication. But next class, we will continue to talk more about divide and conquer algorithm and also cover the full details about integer multiplication, matrix multiplication, and I think maybe another example, I mean, a very important example of Fourier transform that use the divide and conquer strategy. Okay, so any final questions? Sure.
About the last algorithm,
Karasuba algorithm.
The algorithm only makes sense when n is very large. Actually, normally we don't need to do some kind of a large number multiplication. Normally, like we need to be for 64 bit multiplication. So I'm thinking about if we are doing some flow of double multiplication, whether it's more.
I think, I mean, talk about like whether one thing makes more sense. This is totally something very subjective. So it's a little bit hard to say that it makes sense or makes a lot of sense or it's totally nonsense. I think the point is that many algorithms that we are probably going to discuss, I mean, especially, I mean, for a lot of algorithms that in current literature, they are not so practical. But I personally put Karasuba and maybe, for instance, next class we'll talk about Starazen's algorithm for matrix multiplication. they are more practical than you expected, I think, especially for, I mean, they are, I think maybe integer multiplication, it's a little bit hard to imagine the multiplication of like super long integers. But I mean, for instance, in machine learning, there are definitely multiplication of super large matrices. I mean, in that cases, I mean, Strasson's algorithm then just brute forcing multiply a matrix with cost like NQ, I will discuss next class, is actually such kind of divide and conquer idea is actually going to be helpful. But the state-of-the-art algorithm for integer multiplication and matrix multiplication, they are not as practiced as Karasuba or Strasson, etc. This is basically like a trade-off between. Yes, this idea is beautiful in theory, can be practical in large instances, but the state-of-the-art work, super long paper, super intricate idea, they are not very practical. Short answer, I will answer like that. Okay, so I guess this is the class, and see you next week. Thank you.